has the Applied Mycology Lab, and it's in the Department of Wood Science at Oregon State University. Zone lines are melanin, and they're in a very distinct area, and pigments tend to be the things that diffuse through wood. So these are two pieces of spalted sycamore in various stages of spalting. There's not just one fungus on this at all. There's a bunch of different fungi on here. There are lots of different types, even of just zone lines. What a lot of people don't seem to realize is that there's so many colors of zone lines, and that even if you just say, I like black zone lines, there's so many thicknesses of black zone lines. People have very distinct preferences, and they always seem to think that the one that they like is the most typical, which there's really no typical thickness of zone line. When I see these types of zone lines, this is very Lindquist to me. It's very much their type of zone lines and the kinds of ones that I see in a lot of their work. There's a lot of these very thin, instead of the Sharpie marker line here, these are almost like a very fine-tipped artist pen line. They get really mixed up in one another. They're not just one line on the piece. You see a mixture of the circular and the rounded. You don't see so much of the straight. So all three of these pieces are Mel Lindquist pieces, and you can see the form that's very distinctive of Mel, and a vase shape that's very evocative of pottery and very specific types of pottery. Zone lines are melanin, and they're in a very distinct area, and pigments tend to be the things that diffuse through wood. The East Coast, they have very thin ones. In the Midwest, which is where I grew up, we have these thicker ones that look like they're diffusing in a way into the wood. So there are pigmenting fungi, of course, that leave the blues and the reds and the greens in the wood. And then, there are zone lines, which, you think of as lines, but they're not such different things. There's a very clear evolutionary path between them. There's still a diffusing pigment. Melanin, which is what they're composed of, is just a high molecular weight pigment. So there's still just a pigment that's trying to move through wood. Zone lines in particular have been relatively well studied since about, I think, 1913. These lines tend to not actually be black, which people call them black lines, which is a big misnomer. But of course, they're not called black lines in science. They're called zone lines, although they have much fancier names. Going back through and digging through, scientists figuring out, what they were made of. His last name was Campbell, did a big paper on the zone lines of Xylaria species and Armillaria species, which are both fungi. And he started looking at what made them up, and then as you can follow the sort of evolution of science, what are they? Are they mineral deposits? Are they melanin? What are they? And of course, there are lots of different types, and they are generally composed of melanin, but there's clearly others. It's science, welcome to the world of there's never one correct answer. And we want to understand what the fungi are doing that actually makes them occur. If you understand what it takes to make a zone line, then you can make your own zone lines. And that means that it's not going to be any more, from Mark's childhood, going around and with your chainsaw in the woods, in the cold, and pulling out, down trees and hoping that they have spalting. All that old science literature made it possible for us to sit down and go, all right, so there are fungi, and when fungi get together, sometimes they make zone lines, sometimes they make zone lines for other reasons. And we can look at all this old literature and even the newer stuff that was coming out of Brigham Young University, Lane Phillips' work, where he was doing pairings with white rot fungi to make zone lines, building off of all of that to come up with, sort of a catalog of fungi that quote unquote don't play well together, that make these zone lines. That really helped us be able to understand spalting and study it and start inducing it, which is what started us down the road to actually being able to make spalted wood in laboratory setting. And if you know what you're doing and you know the fungi you're using and you know how fast they grow, when you put them on and if you control all the other factors, then you can stop it before you actually get the rot. And that was really the benefit of using all those old papers, especially some of the studies done by Rayner and Todd and Body, looking at how different stages of successional fungi move in and how they contribute to zone lines. So one of the real treats of this trip has been to get to put my hands on a lot of history. Because of course, Mark has a lot of the pieces, that we talk about in the spalting book and that are just so entrenched with the history of how spalting developed here in the United States. And so this is such an important piece. So take a look at it here. It's got those nice thin zone lines that a lot of people in the East Coast are really big fans of. It's got a fair amount of rot, as you can see. Now this piece, it looks pretty shiny. It's had some experiences in life, but it's actually very, very heavy. And this piece right here is one of the first pieces that went through the methacrylation process. So this is a collaborative piece between Mel Lindquist and Mark Lindquist and Dale Nish, and then his student at the time, Kip Christensen. So if you are only moderately familiar with this, Dale Nish, who was at that's Brigham Young University, was working on a way to stabilize spalted wood. Now, stabilizing spalted wood is just something we do now. Everyone talks about, do you use cactus juice? Do you use CA glues? What do you use? Well, back in the 70s, there just wasn't. You used spalted wood and it exploded on you, or you knew what you were doing, and that was pretty much it. And so Dale and Mel it sounds like they were discussing this. Dale came up with this idea to pressure treat and methacrylate the wood, so put in methyl methacrylate. And that was part of Kip Christensen's research project for his master's degree. And so this is one of the first pieces that was ever methacrylated, and its weight is quite substantial, but it did a really nice job of making the wood a little bit more uniform. You can still see density differences. They're still there. This was very early work, but it's a neat piece of history. And what's even better is that Mark has gifted it to me so I can have it in my nerdy spalting wood collection, which is fantastic. This is not a spalting bin. So on this piece, Mark has put it back in the shavings and it's just giving the blue stain more time. One of the neat things about blue stain is that we classify it as a pigment, but blue stain is actually melanin. And if you'll recall, melanin is what is in zone lines. It's a different type of melanin. Now there's lots and lots of different types of melanin. One of the reasons that it's black, but it looks blue because of the way it's in wood and the way the light hits and bounces off, and that makes it appear blue. But then when you get it very highly concentrated, like what you see here, then you can see it's much more black. And so here, what's going on is the blue stain is getting more heavily concentrated. It's coming in and looking darker. Blue stain is a weird category of pigment. Blue stain it's something in between a zone line and a pigment, because zone lines are melanin and they're in a very distinct area, and pigments tend to be the things that diffuse through wood, which means that they're being excreted by the fungal hyphae. So the strands of the fungi are actually excreting the pigment. But most blue stains, their melanin is actually within their cell, their hyphal walls. Now, not all of it. Some of them, of course, do excrete the melanin, but a lot of them, it's the hyphae themselves that are blue. So when we talk about pigmented wood and we talk about chlorosiboria wood, which is the blue-green, the one that's been used historically the most, that you could, in theory, have a piece of blue-green wood and not find, you could cut into the center and maybe not find any actual fungi, because the fungi are secreting the pigment and the pigment is going into the wood. Blue stains, that's usually not what happens. Usually there are going to be hyphae, and the melanin itself is within the hyphae. Now, of course, this is science, so we always have to say usually, because of course, just like with any living organism, there's always going to be, ones that buck the trend. We've done a lot of work with separating the pigments out from the wood. And on one hand, that's nice because now you can have the pigments in a little jar and you can put them on wood as you will. So you don't have to wait for the fungi to grow. These pigments are really very interesting compounds, and they are very understudied because they don't have any real, well, they haven't until now had any real relevance in science. Most spalting fungi aren't aggressive forest pathogens, so people aren't studying them to control them. They don't cause human health issues, so people aren't studying them to control them. And they, especially with the pigments, they don't occur with enough frequency for them to be really heavily utilized in large pieces. You can grow the pigments and you can grow the spalting, and you take the pigments out. Their properties are so unique. We have a red one, and I'm gonna start saying some Latin names. So we have a red fungus called Cytilidium cuboideum that we call flaming dragon fungus. So you can pick which one of those you prefer. And it is a gorgeous, it's that pink red of box elder. Now, it does not cause the pink red of box elder, but it's that same color. And within its color range, it can do blue or purple or orange or red or pink. And its pigment has never really been looked at. There's an old paper by Galinsky, but that's about it. And we recently found out that it's a crystal, a naturally occurring crystal, brand new to science, so we get to name it. And so all of these pigments, they haven't really been looked at or studied. The blue-green one that comes from Chlorosoboria species, Chlorosoboria aeruginosa and Chlorosoboria aeruginosa, the common name is elf's cup for that. It's that little blue-green cup fungus. It has, we actually have done some preliminary work, and it can be used to make the thin films on solar cells. I mean, solar energy from spalting fungi. There's so much potential here. The pigments can be extracted, and we successfully used them, as decking finishes to help prevent UV. We can put them in paints. They have so many neat applications, from solar cells and biomarkers to paints and home finishes, and of course back to spalting. And that's the best part about being able to be an artist in the sciences. And I guess that's the thrill of bioart too, and the movements of bioart that are happening, is that when you give artists money and facilities, the places you can go with art that you didn't expect to go are amazing. And so maybe in 20 years, the solar cells that you put on your house will be from spalted wood, because the tests we've run show that it just has amazing potential for these particular types of cells. About these pigments that differentiate them so much from other fungal pigments or even synthetics is that they're just so color stable. And you can see that if you look at the artworks from the 1200s, the 1300s, the 1400s, I mean, even from the 1800s, all of the other pigments that were put on the wood have faded, and the rest of the wood is just brown. But that blue-green, The blues from the blue staining fungi, the zone lines, they're all still there and they're still quite bright. And so that's, I mean, from the 1200s to today, that type of color fastness, that's unheard of. And we see that too. We see it with our reds, we see it with our yellows. All of these spalting fungi, they hold a very distinct ecological niche. So they have, they've adapted and evolved, these fungi have over millennium, to have pigments that are they're very sticky, that are very resilient, that don't move with water because they have to stay on the wood to protect the wood for the fungus so that other fungi can't grow. And it's those really unique properties that make these pigments so useful for us because, they're naturally occurring, so they're not synthetic. When art and science come together, when spalted wood and the art and science sides are together, now all of a sudden we have solar panels. I mean, we have dyes, we have pigments, and we have a wonderful history of art that we're not forgetting anymore. And that's why art and science have to always be together. Spalting has never been, it's never been something that's been able to really draw grant dollars. And because we've been able to do all this background research and explore these other areas, now industry is starting to take interest. With a group of other researchers, we got an $800,000 grant from the Walmart Foundation to look at using the fungal pigments as textile dyes. Now it's serious. Now we're starting to get grants. Now, people, industry, the National Science Foundation, they're looking at this stuff and going, okay, so that is interesting, and you do have the preliminary look, so let's see what the possibilities are. If you want something that isn't going to fade, these pigments don't fade, and we probably have the longest running study on them because we have pieces from all the way back in the 1200s. We've used them as textile dyes. We're actually working right now with putting them in inkjet printers to print textiles. We've had some good luck with that. But the initial fabric testing we did with them, there are some fabrics that you put these pigments on. Polyester, which is notoriously hard to dye, the pigments work very well on polyester. And you can wash them in hot water and then bleach them and the pigment is still there. I mean, can you imagine not having to worry about bleach accidentally getting into your clothes and bleaching out the color? The pigments are, they're so permanent. And that's just not, it's just not something we have right now. When we jump, and it moves into something completely different. I would suspect that at some point we're going to start looking at the pigments in terms of cancer research. I could see them, somehow being utilized in cancer research or as medicine. I could see that may be happening in the future. I think in the short term, we're going to start seeing them become much more prevalent in terms of, you're going to see paints, you're going to see housing paints and decking and things because of the UV resistance, car paints even. I think we're going to see a big explosion of artist paints. But definitely in the future, once we move past solar, I think, and anything that ties with solar, so anything that has lenses, Mark's very excited about the possibility of especially chlorosiboria being used for camera lenses. And I could see that happening, definitely. So lenses, films, and medicine, I think, are going to be really neat. And wouldn't that be a great thing, to go from this alchemy, this old guild secret, and bring it all the way back around again to medicine and full circle.